So in this video, we're going to find the time domain representation of two sine waves. So you can see here we have a blue sine wave and a red sine wave. And so the blue sine wave, we have one cycle, and then we have two cycles. But for the red sine wave, we basically just have one cycle. Okay, there's maybe a little bit more than one cycle showing here. All right, but for the blue waveform, we have two complete cycles and then maybe a little bit extra showing. So what we're going to do is we're going to write the time domain representation for both of these. So we have to find the magnitude. Well, it turns out that the magnitude of both of these, the peak value of both of these waveforms is simply 1. So this is 1 volt. See the units over here. So this is 1 volt. So the peak value, V peak, is simply 1 volt. So if we were putting that in Blackboard, we would put in something like 1.00 volts. And the next thing we need to do is find the period of the waveform. So if you look here, we're going to start at when it crosses over 0, and we're going to go one complete cycle. So we go one complete cycle. So this is the period. This is the time for one complete cycle. Okay, so remember, period should be a capital T. And so that period is, it's crossing over here at 10.12 seconds. So that's 10.12 seconds minus where it starts, and it's actually starting over here at 0.1 seconds, so minus 0.12 seconds. So the period of the blue waveform is 10. Okay, so the period of the blue waveform is 10 seconds. So again, if we're going to put that in Blackboard, we would put in 3 digits, so we would be putting in 10 seconds. So we have 1 volt and we have 10 seconds. So the next thing, though, that we need to find is where it's crossing over 0 at. Okay. And so we see that it's crossing 0 10 seconds. It's crossing 0 10 seconds after time t equals 0. So the sine wave is starting to go positive. It's getting a little messy in here, but it's starting to go positive 10 seconds after, or not 10 seconds, 0.12 seconds, sorry. 10.12 seconds after 0. And so, but it's taking, for it to make a complete cycle, it's taking 10 seconds, right? It's taking 10 seconds to do one complete cycle. So the phase shift, theta here is going to be the total time, okay? The total time, which is 10 seconds, okay? The total time is 10 seconds, okay? So we're going to divide by the total time for one complete cycle, which is 10 seconds, by the amount of time it takes for it to begin crossing 0, which is 0.12 seconds. Okay, so the seconds cancel out. Now we're going to multiply that times 360 degrees. So the unit for that's going to be 360 degrees. So we'll flip over here to our Octave software. And I'm just going to clear this. So we have 0.12 divided by 10 times 360 degrees. And so our angle is 4.32 degrees. So the angle is 4.32 degrees. And so if we wanted to write the time domain, again, this is the time domain representation of this waveform, we would write lowercase v of t. It's a voltage, which is a function of time, so it's changing with time. And it's 1 volt, so it's be 1.00 volts times sine. Okay, and omega, remember that omega is the radian frequency. So omega is 2 pi f. Okay, and we didn't actually calculate f. Remember that f is equal to 1 over the period. So if that was 10, then f would be 0.1. Okay. All right, so omega is 2 pi f, so it's 2 times pi times 0.1. So 2 times pi is, of course, 6.28. And then we multiply that times 0.1, so it would be 0.628. That's our 3 digits. Okay, and remember the units for that are actually radians per second. Okay, and then we're going to multiply that times time, and then we're going to put in our angle. All right, and the angle, it's coming after 0. Okay, so the blue waveform is not crossing 0 and going positive until after time t equals 0. And so therefore that's a negative. So it's a negative 4.32 degrees. So this blue waveform can be written in the time domain as V of t is equal to 1.00 volts times sine of 0.628 radians per second times time. So remember, time is evaluated in seconds, and so the seconds cancel and you're left with radians. And then we write the phase shift. This is our phase shift. Sometimes we use a symbol theta for that, or sometimes we use a symbol phi, but this is the phase shift. Okay, and the phase shift is 4.32 degrees. So we've got our time domain representation of the blue waveform. And remember, the blue waveform here is actually crossing 0 after time t equals 0. Right down here is time t equals 0. And the blue waveform is actually crossing 0 after that. And so that means that we have this negative sign over here. Okay, because it's after that, so it's behind. Now the red waveform, now let's look here again. The waveform, number one, it's crossing before t equals 0. So it's crossing before t equals 0, so it's going to be a positive phase shift. All right. But before we get to the phase shifts, we also have to look at the time. Okay, the period of this waveform for one complete period. Okay, one complete period here, t is going, it's ending at 19.7, so we're going to take the end time, 19.7, minus the beginning time, which is actually a negative value because it's ahead of 0. So it's going to be a minus 0.29, and we see that the period of the red waveform then is actually 20 seconds. So it'd be 20.0 seconds if we're going to enter that into black. So the frequency is 1 over the period. Capital T is the period. And so for the red waveform, that's a 1 over 20, which is 0.0500 seconds. So if we're going to put this into Blackboard, then we must write this as 50.0 milliseconds. Okay, so if I was asking for the frequency of the red waveform, it would be 50.0 milliseconds. Okay, that's millihertz. Okay, period is seconds. Okay, so the period is seconds. The frequency is cycles per second, which we used hertz for that. All right, so it's 50 millihertz. All right, and so if we wanted to calculate omega while we're doing it here, we'll calculate the omega then. Remember that omega is 2 pi times f, and so it'd be 2 pi, 6.28, so on, times 50 milli. Or you could kind of do it the other way and be 2 pi divided by the period, which you're dividing by 20 then. So you would have 2 times pi divided by the period, which is 20, right? And pi, of course, is 3.14159. So omega would be 0.314,159, and so if we're going to put this, and then of course the units for that is radians per second, but if we're going to put this in Blackboard, we just need 3 digits. So in Blackboard, it's going to be 0.314, and then units would be written as radians per second. Okay, so that is our frequency. We already talked about the magnitude, right? The magnitude, the peak values is still 1 for the red waveform too. So they both have the same peak value. So now all we have to do is calculate this phase shift. Okay, so remember that this thing is taking 20 seconds for one complete cycle. And it is starting to cross over at minus 0.29 seconds. So what we need to do is we're looking at the amount of time that it's crossing over before time t equals 0. Okay. And so therefore the phase angle, call it theta again, what we're basically doing is taking a percentage, right? The entire time for a complete cycle, right? The entire time for the complete cycle is 20 seconds, and the time for it to cross is 0.29 seconds, and then we're going to multiply that times a full cycle, which is 360 degrees. See, the 360 degrees is a full cycle, and the 20 seconds is also a measure of the full cycle. So we're, this is basically 1. You're multiplying times 1. What we're doing is changing the units. Okay, so one complete cycle is 20 seconds, and we're crossing at minus 0.29 seconds, right? So the seconds cancel, and we're left with degrees. And so again, we're basically taking like the percentage of that. So if we were to calculate that, then we would have our 360, I'll multiply first, times the 0.29. And I'm not worried about the negative because we already decided that it's crossing ahead of time. So we know that it's, you're going to have a minus minus and then it becomes a positive because this phase angle is ahead. And then we're going to divide by 20 and we get that to be 5.22 degrees. Okay, so that phase angle then is 5.22 degrees. So when we write this, so if we're going to write the red waveform then, V of t, okay, and maybe I should just write this as red in case you're having trouble determining that. So V of t for the red, again, the peak value is 1, so it's 1.00 volts times sine of omega, and omega is 0.314 radians per second. And then we would multiply that times the time, and then we have our angle. And again, like this one is ahead, and so we end up getting like a minus, so it becomes a positive angle. So it's going to be a plus, let the screen catch up to me here, plus 5.22 degrees. And so here in this example, again, what we did was we looked at the time it takes to make a complete cycle to find the period. And then we found the phase shift, right? Because we know that one complete cycle is 360 degrees. And then we multiply it times the time where it first begins to cross over. And if it's crossing over before time t equals 0, we're going to end up with a positive. And if it's crossing over after t is equal to 0, we're going to end up with a negative in the sign there. So the negative indicates that we're crossing 0 after time t equals 0.